One of the most fruitful ways to think about what functions are and what they do is to think of them like input-output machines. If I have a function, I can take an input from its domain, put it into the function does something to it, whatever, and then it outputs a value in the codomain of that function. Input in, output out. And when it's a function, every input has a unique output that's associated to it. If we think about functions in this way, it also allows us to take two functions, and if they're compatible with one another, we can connect them, chain them together, the output of the first feeding into the input of the second. When we do that, we get a construction that's called a composite function, which we can think of in terms of each of the two component parts separately. Or we can think of it as a single machine with the output and input glued together, taking the input of the first, spitting out the output of the second. That's the viewpoint that we want to start looking at functions with in this section. So why would we want to do this? It's winter right now in Bridgewater, and so maybe I have a function that tells me, based on the time of day as the input, hours past midnight, tells me what is the outside temperature at that time of day in degrees Fahrenheit. So that's a function, because at any one given time, the temperature outside is a single value. It can't be both 25 and 35 degrees at exactly the same time in exactly the same place, right? So this really is a function. And then suppose I have a second function. And the second function's job is to tell me, based on what temperature it is outside, how much energy is my oil-burning furnace at home going to be consuming? What's the energy consumption rate going to be in kilowatts? So maybe I have a function for that, because the outside temperature directly can tell me, uniquely, how much energy my furnace at home is going to have to consume. What's the rate of energy consumption? So for example, if it's 20 degrees outside, it looks like my furnace is probably consuming about 8 kilowatts of energy to heat my home. Right? So I have each of these two functions, and I can understand them each separately. I can ask them each separate questions and get separate answers. But there are cases like this question where we might have to use both of them in combination. If I were to ask you, at 5 a.m., what is the rate of energy consumption going to be to heat my home? That's asking me a question involving the input of my first function, my function that turns a time into a temperature. But it's asking me about the output of the other function. This is the function which takes a temperature and tells me an energy consumption rate, right? So what I really want to be able to do is I really want to be able to connect these two functions together. And I can do that if and only if the kinds of outputs that the first function generates are the same as the kinds of inputs that the second function expects. In other words, I can't connect these two functions together unless the output of the first is able to be fed in to the input of the second. If the codomain of my f matches the domain of my E. And in this case, that answer is yes, because the codomain of F consists of all of the possible outdoor temperatures that we can have, and the domain of E also consists of all the possible outdoor temperatures that we can have, right? So the codomain of the first function matches the domain of the second one, and that allows me to connect these two up by directly taking the output from my first function, which we're calling f of t, right? I feed it a time, it gives me a temperature, and then I just feed that temperature directly into the second function. And it's going to then output for me an energy consumption rate. In doing that, what I've really done is I've created what we're now going to call a composite function. And a composite function we're going to think of as the single machine now. The single function that takes in my time and spits out my energy consumption. And along the way, but now we might not be able to always see it, we're going to turn that time into a temperature and then turn that temperature into energy, right? But if we're just looking at the composite function from beginning to end, we might not always see that temperature that's happening in the middle, and we might not care. How might we get this information out of the graphs for these functions? Well, 5 o'clock a.m. represents, in my first function, an input value of t equals 5. It's 5 hours past midnight, right? So t equals 5 is how I operationalize the concept of 5 a.m. So then I'll take my first function, my f function, which takes a time and spits out for me a temperature in Fahrenheit, and I'll use it to spit out the temperature at 5 a.m. So I'll plug this value of t into my function using my formula, using my graph, however we do it. And in the middle, we can say that at 5 a.m., the temperature was about 34 degrees Fahrenheit. My first piece of my function told me that. So this 34, that's going to be my intermediate value, my intermediate step that I get right here. But in the composite function, the thing that happens next is that that value gets immediately fed in to the second function, which is going to take a temperature and produce for me an energy consumption rate. And so what I end up getting here is taking that same 34 degrees Fahrenheit that I got out of the first function and putting it in to the second function on its input axis, I can do that again because the domain of this function consists of the same kinds of temperatures that we can get as the outputs of the first function. Otherwise, we can't connect these two up in this way. So I'll plug 34 degrees into my second function, and either using the formula or using the graph or whatever, get the output value that turns the temperature, 34 degrees, into the energy consumption rate to heat my home, 5.2 kilowatts, give or take. And so, written out in English, what we've just done is use this composite function to tell me that at 5 a.m., the energy consumption to heat my home is going to be 5.2 kilowatts. But the way that we did that is we went through this intermediate step where we used the time to tell me the temperature and then used that temperature to tell me the energy consumption rate. That's what a composite function does. It gives us this intermediate stopping point along the way that we can choose to see when it's important to see it, or if we don't care, we might just gloss over it. What is this going to look like in a formula? Well, in our formula, we need to be doing exactly what this sort of schematic diagram is telling us that we're doing up here. Taking the output of my first function, f of t, and making it the input of my second function, which I'm calling e in this example. So, the single function which we call e of f, or e composed with f, or e after f. Some ways of thinking about this. We can write a formula for that just by taking the e function and feeding the e function an input which is equal to the output of the f function. So e of f of t. What is f of t? Well, if we have a formula for f, we know what that is. F of t, if f of x is this formula, f of t is that formula with t's in place of x's. And so what we're saying is we're going to plug that expression, f of t, into the input of my e function. So I want e of this whole business. How do I do that? I make that whole business stand in for the variable through which I'm defining a formula for e. So if e of x is 12 minus 0.2x, then e of this stuff is going to be 12 minus 0.2 times that stuff. 25 minus that expression involving t's. And so what I get at the end of this process is a formula for e of f of t. And I can ask this formula directly, if it's 5 o'clock in the morning, so if t equals 5, what is the energy consumption it takes to heat my house? Just by replacing all the t's by 5s and getting my 5.2. So that's the power of having a formula for the composite function, is it allows us to skip this intermediate step when it's convenient. The downside is that it skips that intermediate step. And so one of the skills you're going to practice in this section also is being able to take a sort of a complicated looking formula for a function and identify, well, what might be two pieces, the first function and the second function, that I can break that apart into. And I'm using the word chained together here for two reasons. First, because it gives us this nice picture of connecting the output of the first to the input of the second just in a direct chain to one another. But second, because when you get to calculus and you study these kinds of functions that are made up of two smaller pieces in this fashion, there's a rule in calculus called the chain rule that tells you how to do calculus with composite functions if you know how to do calculus on the two individual pieces. So as you're thinking about composite functions in this section, keep that word chain somewhere in your memory banks, because when you go on to calculus next semester, that is the cue that you're going to have, that these are the types of functions that the chain rule in calculus applies to.